The last thing we need to talk about is deviations from the ideal gas law. So, we talk about this ideal gas law, we tell you PV equals nRT, we tell you different ways to calculate different things and understand how all of these individual gas laws are intertwined and related to form our combined gas law, get us our overall parameters, etc. But why do we call it ideal? Well, not all gases behave under ideal conditions, and we're going to talk about what that means. So you need to be able to explain deviations of real gases under non-ideal conditions. Identify the components of the van der Waals equation that are used to modify the ideal gas law. So deviations from ideal behavior. What is an ideal gas? Well, an ideal gas is any gas that actually obeys our ideal gas law. It's behaving in an ideal fashion. So what does it mean for a gas to deviate from ideal behavior? It means under the same conditions, it does not obey the ideal gas law. Most gases will deviate from ideal behavior at high pressure and low temperature. It's easy to remember because at high pressure, low temperature, gases will always condense. The higher the pressure, the more closely those molecules are to one another. The lower the temperature, the less energy those molecules have to move. Both of those conditions will lead to a molecule turning to a liquid or even a solid state under the right parameters. So every gas has where it will behave under what we consider to be non-ideal conditions. Under non-ideal conditions, it is no longer behaving as an ideal gas, it is behaving as just a gas in general, and we have to take those other parameters into consideration. But what parameters are those? To really understand why gases deviate from ideal behavior, I need you to recall two of the postulates of the kinetic molecular theory. The first postulate that we're going to recall is number 2, where we said the volume of gas particles is so small we can usually ignore it. That is true. We can usually ignore it. The thing is, gas particles do have an actual measurable volume. So they can deviate based on this actual volume. Gases deviate from ideal behavior at high pressure because at the high pressure, the volume of the molecules matters. The molecules become so close to each other, we can't ignore their volume anymore. So think about if you're putting something under pressure. It's pushing down this piston, and I've got these gas particles here. The more I push down on that piston, say I lower the system to here, the more I push down, the closer these molecules will be to each other, the less that I can ignore their volume. I also need you to recall number 4. Postulate number 4, attractions between gas particles are so small we can usually ignore them. True, but the thing is, attractive forces between gas particles do actually exist. And if we lower the temperature of the system, the gas molecules start moving more slowly. So the intermolecular attractions between the molecules becomes more important. What I want you to think about is put yourself back into your high school hallways, and you've got a really fast passing period before you just got out of one class, you've got to get to your next class, you've only got 3 minutes to get there, you don't have a lot of time to slow down and really see the people you're around. So you may or may not see your friend rushing down the hallway past you. You're moving so fast. I've given you a higher temperature, you have more energy, you're moving faster. Let's say that instead we lower your increase your passing time to 8 minutes. Correlate this to temperature. I've taken away some of your temperature. I've cooled down your system. You're moving slower. You have 8 minutes to pass to get to your next class. You see your friend. What's the likelihood of you stopping to talk to them? A lot higher because now you have the time to do so. So I realize I'm talking about time versus temperature, but I want you to think about the molecules in terms of temperature. The slower they are, the less energy they need. The slower they're moving, the more they're going to fear those attractive forces to one another. So at lower temperatures, the attractive forces between the molecules themselves, the intermolecular forces, actually becomes a lot more important because they start to sense each other more, they start to interact more, and it slows down the overall molecule. To correct for all of this, we have what we call the van der Waals equation. The van der Waals equation is an attempt to correct the ideal gas equation for real gases. Here we've got pressure plus AN squared over V squared times, so let me zoom in here. N is still moles. V is volume. A and B are constants. P is pressure. So, get this, there you go. Okay. So the pressure correction, where I've got pressure plus AN squared over V squared, this pressure correction is applied because the pressure exerted by the gases is less than it would be if there's no attractive forces between the molecules themselves. Because of those attractive forces, they're holding together not really as individual particles anymore, but kind of as an agglomerate of particles. So the true pressure of the system is less than we ideally would be. So we need to correct for that difference. The second correction we see is a volume correction. We've got volume minus N times B. This is because the volume available to gas molecules is less than the volume of the container because the molecules themselves take up space. So we're adding in, based on the number of moles we have, we're adding in a correction to pressure to account for the attractive forces of the gas molecules. And for volume, we're subtracting out the volume of the gas particles themselves. A and B, again, are just constants. These are experimentally determined for each gas. You would not know these by heart, okay? If required, I will give them to you. You do need to know the van der Waals equation. You do need to understand this equation. You need to be able to use this equation and explain where the different corrections come into play and why. The constant A is a measure of the attractive forces between the gas molecules. So we've got the correction to account for the attractive force affecting the pressure of the system. The constant B is a measure of the volume of the gas in the molecules. So again, the corrective force in the volume because the molecules do have an actual measurable volume. For example, for two different systems here, we've got helium and carbon tetrachloride. For helium, we see the A and B constants, A 0.0342 and B 0.02370. Basically, very little correction needed or necessary for helium. But for carbon tetrachloride, we have an A value of 20.34, a B value of 0.1383. This is showing me that carbon tetrachloride has a very large attractive force. It is going to agglomerate. Those molecules are going to stick together and attract to each other, have those forces holding them together as more than one particle a lot stronger than, say, a helium atom. B, volume is definitely bigger as well. Carbon tetrachloride is just a bigger molecule than helium is. And for a quick example, under what conditions would chlorine gas be the least ideal? High pressure, low temperature, high pressure, high temperature, low pressure, high temperature, or low pressure, low temperature. Well, it's going to be least ideal under high pressure, low temperature, because that's where it's going to deviate the most from the ideal gas law. Again, you do need to be able to explain the van der Waals equation, use the van der Waals equation, explain the corrections, and understand where they're coming from and why they are necessary. In order to use the equation, I would have to give you the values for A and B, and at that point it's a plug and chug type calculation, but you do need to be able to explain the different parts of it as well.